Good morning and welcome to this next lecture on vibrations of plates and shells. So last class we came up till the formulation of force and moment resultants. Now let us go ahead with Hamilton's law. Okay. Okay. So the form of the Hamilton's law is the variation of this integral between two time points of this action, which is the potential energy minus the kinetic energy minus other terms, which are, let us say, the boundary term and the loading term, dt is equal to 0. Okay. Now what is W in? W in is the energy that is coming from the boundary forces plus the external loads. Okay. So let us begin with the kinetic energy term. Kinetic energy term. Okay. So the kinetic energy dk over an element is 1/2 rho u1 dot square plus u2 dot square plus u3 dot square. These are big U's. Okay. Each is a function of alpha 1, alpha 2, alpha 3 over a differential volume dV. Okay. So now over the entire structure we have K, that becomes rho by 2 integral over alpha 1 integral over alpha 2 integral over alpha 3. Okay. Now we use the love assumptions of any big U being equal to a small u plus alpha 3 times beta. Okay. So you have small u1 dot squared plus small u2 dot squared plus small u3 dot squared, which is the same as big U3. Now the alpha 3 square beta 1 dot square plus beta 2 dot square and the cross terms plus twice alpha 3 u1 dot beta 1 dot plus u2 dot beta 2 dot and the length elements A1, A2. Let us for now put it this way for completeness. We are going to drop this alpha 3 by r term anyway, d alpha 1, d alpha 2, d alpha 3. Okay. Now if we do the alpha 3 integral, which is from minus h by 2 to h by 2, this only this term carries alpha 3. So it becomes alpha 3 square by 2 over the limits minus h by 2 to h by 2. Okay. So therefore this will go to 0, right, because it is h square by 4 minus h square by 4. So this term will go to 0 if we do the alpha 3 integral. Now this will acquire only one h, and this will acquire h cube by 12. Okay, so my k becomes rho h by 2. Let me lower it. K becomes rho h by 2 integral alpha 1 integral alpha 2 u1 dot square plus u2 dot square plus u3 dot square plus I have one h here, so I am doing h square by 12 beta 1 dot square plus beta 2 dot squared. A1, A2, d alpha 1, d alpha 2. Okay. So we will now go ahead and take the variation of this. So the expression is integral t1 to t2, the variation of k dt. Okay. So that results in so we straight away eliminate the 2, integral t1 to t2 integral over alpha 1 integral over alpha 2 twice u1 dot. So we have removed the 2. So u1 dot delta u1 dot plus u2 dot delta u2 dot plus u3 dot delta u3 dot, okay, plus h square by 12 beta 1 dot delta beta 1 dot plus beta 2 dot delta beta 2 dot A1 A2 d alpha 1 d alpha 2 dt. Okay, so we will take one of these terms now and do a time integral on that. Okay, so we will take integral t1 to t2 u1 dot delta u1 dot dt, okay, which we will use the product rule now. Okay, so that is equal to u1 dot delta u1 between times t1 and t2 minus integral from t1 to t2, the derivative is transferred delta u1 dt. Now Hamilton's law says between 2 points, 2 time points where the states are known. Okay. So once the states are known, the variation is 0. So this boundary term, the time boundary term, goes to 0. Okay. So that means integral t1 to t2 u1 dot delta u1 dot dt is equal to minus integral t1 to t2 u1 double dot delta u1 dt. Okay, so that is what we have. If we now follow this logic, the entire kinetic energy variation term looks like minus rho h integral T1 to T2 integral alpha 1 integral alpha 2 u1 double dot delta u1 plus u2 double dot delta u2 plus u3 double dot delta u3 plus h square by 12 beta 1 double dot delta beta 1 plus beta 2 double dot delta beta 2 A1 A2 d alpha 1 d alpha 2 dt. Okay. Now, as I said, we are working at the level of Euler-Bernoulli beam theory. Or at the level of Kirchhoff plate theory. Okay. So, as a result, we will ignore rotational inertia. Okay. So, that means this term will go to 0. This term contributes to the rotational inertia, therefore this term is ignored. Okay. So, the net effect of the kinetic energy term. So, we have to remember the signs as well. So, T1, T2 delta k dt is minus rho h T1 T2 integral alpha 1 integral alpha 2 u1 double dot delta u1 plus u2 double dot delta u2 plus u3 double dot delta u3 a into a1 a2 d alpha 1 d alpha 2 dt. Let me mark it in some color. We will need this later. Okay. Now, the boundary loading, the external loading term, okay. The external loading term looks like this. EL, the external loading, is actually integral alpha 1 integral alpha 2. Okay. This is force per unit area U1 plus force per unit area in the 2 direction U2 plus force per unit area in the 3 direction U3 into A1 A2 d alpha 1 d alpha 2. So, the delta EL becomes integral alpha 1 integral alpha 2 q1 delta u1 plus q2 delta u2 plus q3 delta u3, a1 a2 d alpha 1 d alpha 2. Okay. If I put the integral t1 to t2 dt, I put an integral t1 to t2 and a dt. Okay. So this is an elemental force, okay, over a1 alpha 1 and a2 alpha 2, that, okay, and it's an elemental force, okay, and u3, so this term, that is the work done, that's the work done, and therefore this is the variation, this is the variation. Okay. So then we have the boundary term, we have the boundary term, okay. The boundary term, the boundary energy comes from, okay, so we have the, let us say we have alpha 1 and alpha 2, okay. And let us say this is the element, okay, this is the element, okay. So along this what we have is an external force, okay, elemental external force into U2, okay, force per unit length, okay, force per unit length into U2, okay, into the length element A1 d alpha 1. So this is a N22, let us say, normal force resultant. So force per unit length into the elemental length and the displacement, okay. So similarly we have N21, so we will put a star for the external load into U1 into A1 d alpha 1. So N21 is on the 2 phase in the one direction, so it will be in this direction. This is N21 star, okay, and therefore is goes with the U1 displacement. I will clarify in just a moment. Plus you have Q23 star, okay, on the 2 phase in the 3 direction, 2 phase in the 3 direction. So this is the one phase, okay, normal to alpha 1. This is also the one phase normal to alpha 1. This is the 2 phase normal to alpha 2, okay. Alpha 2 axis is normal to that phase, and this is also the 2 phase. So Q23 on the 2 phase in the 3 direction multiplied by U3, the vertical displacement, into the elemental length, okay. Similarly the moments, okay, there is an M22 moment which works like this, There's an M22 moment that works like this. For 3. Okay, so that is M22 star into beta 2, okay, then A1 D alpha 1 plus lastly M21 the shear moment, okay, then beta 1 A1 D alpha 1. Okay, so there are 5 terms on the alpha 1 phase. Okay, so the EB will be an integral over the alpha 1 phase, and there are 2 alpha 1 phases. Okay, there are 2 alpha 1 phases. So you have these 5 terms. So let me just give you a picture here. This is not the entire boundary force. There will be a force coming from this phase also, that phase also. So let me first give you a picture, then we will see. Okay, so we have alpha 1, alpha 2. Let me build an element around it. Yeah, let me build an element around it. So we get this. Okay, so that's the middle surface. Okay, so this is alpha 1, that is alpha 2, that is alpha 3. Okay, so we will do the normals first. Okay, so we have N22 star that way, and there will be an N22 star this way. Okay, in the static case they will balance, or there is a balance equation. In the dynamic case there will be some variations, but this is just to show the resultants. Okay, so then we have N11 star coming here, and N11 star. So we follow a convention on the negative phase. This is the incremented alpha 2 phase. Okay, this is a negative alpha 2 phase. This is the incremented alpha 1 phase, that is a negative alpha 1. So on the positive phase, N11 points in the positive direction. So that is the convention we use. Okay, so then we have shear force resultants. Shear force resultants. Okay, they will be, let me use the red color, no, blue itself. So this is a shear force resultant. It is on the one phase in the 2 direction. Okay, so this will be N12. Similarly, there is a shear force resultant N12. Okay, this is on the 2 phase in the 1 direction. So this will be N21, okay, and that will be N21. Okay, and then we have the vertical shear force. Caused by sigma 13 and sigma 23. This is caused by sigma 12. Okay, again on the negative face it will be downward. Okay, this is the 2 face in the 3 direction. This is the 2 face in the 3 direction. Okay, then this is the 1 face in the 3 direction. There is a 1 face the 3 direction. Okay, so without cluttering now, if I was to show you the other resultants. Okay, so again we have alpha 1, alpha 2, alpha 3, and let me build an element around it. Okay, so let us say this is my alpha 1, that is again alpha 2, this is alpha 3. Then my moment M11, okay, M11, this will be the M11 moment. Okay, that will be the M11 moment. Okay, the diode using the right hand rule would be going that way. Okay, the diode will be pointing that way. That's kind of confusing. Similarly, M22, this is M22, this is M22. Okay, the positive moments give negative curvature. It will turn out that that is the right convention. Okay, these are positive moments, they give the curvature downwards. Okay, then the shear moments. Okay, the shear moments will be on the one face in the 2 direction will be like this. So let me take blue itself. So they will be like this. This is in the plane of the face. This is again in the plane of the face. So this is one face 2 direction M12. This is M12. Okay, this is 2 face in the 1 direction. This is in the plane of the face M21. This is in the plane of the face M21. Okay, so you have these resultants. You have N11, N12, N22, M11, M12, M22. Okay, and then Q13, Q23, and N21 and M21. Okay, these are the 10 resultants. Okay, let me stop here. The time is run out. We'll continue from here in the next class. Thank you.